made it. So this is your synthesis. The synthesis will require you guys to take this salt, add ethylene diamine under certain conditions, and then get 3 possible salts out. Okay, so this first part is just the objective. You basically, for this portion of the lab, you guys are going to synthesize nicoethylene diamine, aqua sulfate salt. Again, the reason why we call it a salt is because there's a cation and anion. This whole thing in brackets right here is the cation. This SO4 is the anion, and then you can have water hydrated sticking to that um, compound. And the formula is going to be 1, 2, or 3 ethylene diamine. Ethylene diamine, EN, is short. It's an abbreviation for a organic chemical that will latch on to nickel. Okay, so this is the synthetic scheme. You guys will take this, which is a green solid. It's nice green crystalline solid. This is the formula, nickel sulfate hexahydrate. And then you're going to add this chemical. And we abbreviate this chemical because you see how complex it is to draw? We label it EN, short for ethylene. This is the ethylene part. 2 carbon is the ethylene diamine, because this ammonia type structure is called an amine, and there's 2 of them. That's why it's called ethylene diamine. Ethylene diamine is going to go in here, kick off these waters, and replace 2 of these waters. And so what we do is we abbreviate this ethylene diamine to look like this, where the nitrogen is bonding to the nickel. And then you see these right here where it bends, those represents carbon. Okay, if you take organic chemistry, this is called the line notation, where we just draw lines, and wherever there's an end of a line or a bend in the line, it represents a carbon. Carbon always has 4 bonds. So the fact that this carbon right here has 2 bonds already means that there is a hydrogens that are attached to this. Okay, so this is the first substitution. This would be salt A. And then in the second synthesis, you have a higher amount of ethylene diamine in the reaction mixture. And you would get that, where 2 ethylene diamines now substitute for 4 waters. Notice that the nickel is a +2. The ethylene diamines are neutral. So the nickel is still +2. In order to counteract this +2, you need a -2 sulfate. That's the salt. That's the negative, and that's the positive. And then there's still a water here, and we draw water as OH2 to show that the bond is actually towards the oxygen, but it's still H2O. Okay, there's also a side product here, and this chemical is different from this chemical. You notice how the water are next to each other in this chemical? It's called the cis isomer. These waters are opposite each other. It's called the trans isomer. You guys are generating the cis isomer in the synthesis. Okay, and then if you change the reaction conditions in such a way that you have an even number of nickel and ethylene diamine, then you might get all 6 waters being removed, and you get 3 ethylene diamine. And you notice how different these solutions are? That's because these are 3 distinct products. So this is the synthetic scheme. This is the strategy that you guys are going to be doing in this particular reaction. Okay, so the possibility is, these are the structure. The sulfate, that's your starting material. That's NiH2O 6 times. 1, 2, 3, 4, 5, 6. Okay, sulfate, and then it's a hexahydrate. If it's a hexahydrate, there are 6 waters that are not bonded to the nickel, but are attached as a hydrate. If you heat these things up, those waters will be removed, but not the waters that are bound to nickel. They need more energy. The first substitution looks like this, X equals 1. The second substitution looks like this, X equals 2. And the third substitution looks like this, X equals 3. Okay. In terms of um, I'll get to your chat question shortly as soon as I finish this discussion. In terms of synthesis A, you guys are going to start with 5 mils of water, put it in a 50 ml beaker. You're going to weigh about 1.25 grams plus or minus. In this particular case, I weighed 1.2801 grams of nickel sulfate hexahydrate. And then what I have next is I am transferring it to the water. I'm stirring that right now. And then I'm adding 1 ml of 25% ethylene diamine slowly. And then I stir until the color changes. And then I cool it in an ice water bath and then add absolute ethanol. Absolute ethanol means it's pure ethanol, no water in it. I let it sit in the ice bath for a while until it crystallizes. This is what my product looked like. This is the beaker headshot. Then if I have enough of this, and you notice how murky it is, it means they're solid suspended in water. Then I would set up a vacuum filtration and collect my product. Then I would weigh it. I would dry it overnight and then weigh the product in the next period. And this is what it would look like. Okay. So this is and I recover in this particular experiment 1.2582 grams of my salt A. This is the synthesis for salt B. Again, I start with 5 milliliters of water in a 50 milliliter. I weigh about 1.25 grams of my starting material. In this case, I weighed out 1.2752. I go ahead and put it into the water, mix it up. I add, in this particular case, I add 2.5 mils of 25% ethylene diamine. More ethylene diamine in the second reaction. And then I stir, and then I let it sit in the ice bath. I wait until it crystallizes, set up my vacuum filtration, and this is what the product looks like when it finally forms my precipitate. And then I would go ahead and I don't know what happened there. There's a blur there that shouldn't be there. But I collect it in my vacuum filtration. I go ahead and dry it overnight and then I weigh it when I come back the next period. And in this particular case, I recovered 1.3937 grams of my salt B. And this is the what it looks like when I collect enough. The last synthesis is going to be very similar to the first two. Again, 5 mils of water, except this time I only weigh 1 gram, approximately 1 gram, 1.0703 grams of nickel sulfate hexahydrate. Then I transfer it to my 5 mil water. I add, in this particular case, 3.5 mils of 25 mils ethylene diamine. So I use a lower amount of nickel salt. I use a greater amount of ethylene diamine. Then I stir. In this particular case, I put it in a water bath, wait until it crystallizes, and this is what it looks like. So this is a really colorful experiment. Metal complex, you will learn, are highly colored. And the reason why is because of the transition metal. Okay. And I will go ahead and set up my vacuum filtration, set up my butanol. I would dry it overnight. And in this experiment, I recovered 1.2631 grams of salt C. So that's the synthesis. And this right here is the data table for that synthesis. this is the mass of the starting salt for A, B, and C. This is the mass of the product. So if you know the chemical formula of the starting material, which is NiSO4, and then there should be 6 waters here, 6 waters, okay? If you have that molar mass, then you can figure out how many moles each of these have. For each mole of the nickel sulfate hexahydrate, you produce 1 mole of product. It's a 1-to-1 ratio, okay? It's not a 1-to-2, it's not 1-to-3, it's a 1-to-1. So the moles of your reactant should be equal to the moles of your product. And then all you've got to do now is figure out what is the molar mass of your product based on the analysis. And this is the theoretical yield. This is the actual yield right here. This is what you actually recovered in the experiment. So the percent yield is going to be your actual, that's these values right here, divided by the theoretical, which you guys can't do right now because you need the true molar mass of your product. Okay, so this is our table. The next part of this analysis is going to determine how many nickels I have per salt and how many ethylene diamine you have per salt. And this is the absorption spectrum. You guys did this with the SpectroVis vernier probe. This is a more advanced instrument, but this is the absorbance spectrum for the different salts, okay? And this is for X equals 0, so that would be your nickel sulfate hexahydrate, that's your starting material. This spectrum right here is when there's only 1 ethylene diamine. This right here is when there's 2 ethylene diamine. And this right here is when there's 3 ethylene diamine. Notice they have different wavelength by which the maximum occurs. And that's because they're different colors. The different colors means that they're absorbing light at different regions on the electromagnetic spectrum. That's what gives rise to the different colors. Okay, so that's your synthesis part. In fact, that is that you guys would have been doing today. The 3 nickel ethylene diamine complex that was synthesized in part 1 will be analyzed in this particular part. If you were in lab, I would have you analyze just one of your salt. And the reason why you need to analyze just one of your salt, the one that is most pure, is because it would take too long to analyze all 3. So I would basically look at your salt and say, okay, looks like salt C is the purest among your synthesis. Go ahead and analyze that. Another person, I would say, okay, you will do the analysis for salt A. Since you guys are not doing the analysis, but watching the video of the analysis, you should do all 3 analysis. Once you do one, the rest is easy, okay? So let me go ahead and show you again, this is the synthetic scheme that I showed you in the previous one. I just put that there as a reminder. And then there's 2 parts of the analysis. One is the analysis of the ethylene diamine, because you need to know how many ethylene diamine, how many moles of ethylene diamine are in that chemical. And then the other one is the moles of nickel in that chemical, because if you know the moles of nickel and you know the mass that you have, then you know the percent of nickel in the complex. So I'll go ahead and show you what the possibilities are again. And you've already seen this, but this is what this is your results from the last time. This is a few verbiage on what's happening. This is what's going to happen in terms of your synthetic scheme. It's in a rough form, so let me just show you everything. For each salt, you guys are going to weigh approximately 0.05 grams. Approximately 0.05 grams. So I need to change this number right here to the value you have for each salt. So one of you, if we were doing this experiment, would be doing salt A. Another one might be doing salt B. Another one might be doing salt C. But you will be doing this for the entire period, depending on which one you are assigned. So once you weigh it out, once you weigh about 0.05 grams, you're going to take, and you're doing 3 trials. So for one salt, you do it 3 times. So if you're assigned salt A, you're going to do 3 titrations. Once you have your 3 samples, then you're going to add 10 mils of 0.1994 molar hydrochloric acid. The hydrochloric acid will actually go in, and you see how these ethylene diamines, these are like ammonia? The acid will go in and bind to the nitrogen. It's going to protonate the nitrogen. And these ethylene diamines will come out. But because the hydrochloric acid likes the base of this N group right here, and there's 2 N per ethylene diamine, you need 2 moles of hydrochloric acid for every 1 mole of ethylene diamine. So it's a 2-to-1 ratio. What you are doing in actuality is adding an excess amount of hydrochloric acid. So depending on how many ethylene diamine are in your 0.05 grams, the hydrochloric acid that you're adding is an excess amount. Some hydrochloric acid will not react. Okay, some hydrochloric acid will not react. Well, what does that mean? Well, it means that there's hydrochloric acid. This solution right here is going to be acidic. Okay, what you're doing is you're using methyl red right here as your endpoint indicator. So the excess hydrochloric acid that did not react, that's what you are titrating with sodium hydroxide. That's your titration right here. So what you will do is you have 0.09697 molar sodium hydroxide. You put that in a burette, and you take these chemicals right now. You see how it's sort of yellowish? Well, when you put phenolphthalein indicator, it'll turn reddish. And what you need to do is you need to add sodium hydroxide until that pink turns clear again. And that's where you stop. You stop at that endpoint. Because at that point, all the hydrochloric acid will have been neutralized, the excess hydrochloric acid that did not react. So the way you do this calculation is the excess hydrochloric acid that did not react, you will know how much did not react because you will know the volume of sodium hydroxide that you added and the concentration. So the volume times the concentration gives you the moles of hydroxide. The moles of hydroxide equals the moles of hydrochloric acid that did not react. If you know how much you put in initially and you subtracted the amount that did not react, then you will be able to calculate the amount of hydrochloric acid that did react, that did bind to ethylene diamine. And so the amount of hydrochloric acid that did react, which is the difference between the excess minus the moles of sodium hydroxide at the end point, well, that amount that did react, if you divide that by 2, because remember, it takes 2 hydrochloric acid for every 1 ethylene diamine. If you divide that by 2, then you have the moles of ethylene diamine for your salt. If you now have the moles and you have the mass, then you can figure out the percentage of ethylene diamine in that compound. It's just, you take the moles of ethylene diamine, you use the molar mass of ethylene diamine to get the mass, and the percent of ethylene diamine is just the mass of the ethylene diamine divided by the mass that you weighed out here. I will go over those calculations on Wednesday when all these videos are up. But that's your ethylene diamine analysis. It's called a back titration. The reason why it's called a back titration is because you add excess, sorry about that, acid in here, and the amount that didn't react, you are titrating. If you know how much you add originally and you subtract the amount that was in excess, then you will know how much did react. So I know that's a handful to grasp. It's also written in your lab manual as well as in my PowerPoint, but I will give you the details of that shortly. But hopefully you'll be able to visualize that. That's only for ethylene diamine. Now we need to analyze nickel. The nickel will be based on forming standard solutions. And the standard solutions, they say to take your nickel starting material, nickel sulfate, and make a certain amount of concentration and then do a serial dilution. A serial dilution basically means take your original stock solution and take portions of it and make two other solutions from that right here. You can see in this illustration right here, these are my three. The first one, my most concentrated one, would be my stock solution. And then I would take like 10 mils, put it in a 25 ml vol flask, and then dilute it. I would take my stock solution. I would take 15 mils, put it in another volumetric flask, and then dilute that. And then I would have various concentration. In this particular experiment, I actually did 5. 1, 2, 3, 4, 5 right here. Okay. Then I know the concentration of each one of these. I would measure the absorbance. That's what this graph shows you. I have a known concentration of my nickel from my standard, and I measure the absorbance through the instrument. Now, if I take my salt, and I know how much I have, and I put it in a certain amount of water, and I measure its absorbance. If I measure its absorbance, I can use this calibration curve to calculate the concentration of the nickel in my salt. So that video is not quite up, but that's the idea for the nickel analysis. You're using absorption spectrophotometer analysis to get the concentration of the nickel for the sample that you have. Okay, because these things because you need to measure the wavelength or the absorbance at the intense absorbance, you're required to take the absorbance of all the salts so that you know what wavelength to sit on in order to be the most sensitive. Again, these are the absorbance for the 3 salts as well as the starting material. Okay, this is the spectroscopic analysis. And you can see I had 5 standards here. The concentrations of these standards were 0.015, 0.03, 0.04, 0.06, and 0.07. And the absorbance are right here. The instrument takes 3 readings and takes an average. That's the mean right here. So these are the 3 readings the instrument took, and they take it like in a flash, in like a second or 2. And then, sorry about that, it takes the mean. It gives you the standard deviation of each measurement right here, and the percent relative standard deviation. The main thing that you guys want are the absorbance. That's 0.1456, 0.2244, 0.3041, 0.3871, 0.4576. So if you make this your x-axis, that's your concentration, and you make this your y-axis, that would be your absorbance. Then you can plot these points and get a calibration curve. And this instrument automatically does that. And this is the equation that it got. The absorbance is equal to 5.169 times the concentration of my nickel. That's these concentrations right here. Plus the y-intercept is 0.06771. The correlation factor for this particular data is 0.99943. Recall from a previous experiment that the goodness of fit, how well those points fit the straight line, is the correlation factor. 3 nines is pretty good. Okay, 3 nines are pretty good. If you only have 1 9, that's not very good. If you don't have any 9s at all, that's really bad. If you see right down here, you will see tabs. And those tabs says nickel salt synthesis. It'll say ethylene diamine analysis. It'll say salt A titration, salt B titration, salt C titration, and the nickel sulfate analysis, nickel and sulfate analysis. So this is the data table that you guys will download from Canvas. Okay, let's go to the first tab, the nickel synthesis part. This is basically a summary of what you saw in the first slide. This is the initial mass of the nickel salt that I used. This is the mass of my product. Okay, I only did 1 trial in the synthesis, so all you see is 1 value for the initial mass and 1 value for the final. That's the data for the synthesis. For the ethylene diamine part, here's the different salts: salt A, salt B, salt C. And if you look closely, you will see that the concentration of your hydrochloric acid is up here, 0.1994. Originally, the direction calls for 0.20 molar. Well, we can't exactly get 0.20 molar. We actually was able to get 0.1994. And then the sodium hydroxide, it called for 0.1 molar. Well, we couldn't get exactly 0.1 molar, so we got 0.09697 molar. Okay, these things are in molar. Salt A, we did 3 titrations. We start for the first trial, 0.0515 grams. We add 10 ml of hydrochloric acid at 0.1994, so that's an excess amount. Then we did the titration, and it says for the first trial, see the titration curve to figure out what the equivalent volume is. For the other two, I give it to you. I tell you it's 17.33, 17.25. Let's go to the titration A tab, and you want to go down here. And this is the data for that titration. What we have is, and I carried this titration past the endpoint, okay, because I was recording it through Vernier. So what you have is different volumes, and it records a different pH. Notice that this thing has 2 inflection points, one here and one here. The question I have for you is, why are there 2 inflection points in this titration? Okay, I'm not going to answer that. You guys are going to have to think about it. Think about what chemicals are in your Erlenmeyer flask and what chemicals are being protonated when you do the titration. The key here is that when the methyl red changes color, it changes color right about 4.2 to about 5.0. So this is the volume right in here is where you want to read the equivalence volume for the titration of the excess hydrochloric acid. This portion right here, this first inflection point, not the second, the first. Okay, you need to be clear on that, because if you're using the second inflection point, it'll be way off. You gotta use the first inflection point when the indicator changes color. So that's salt A. You guys have to figure out what volume this particular inflection point is, because that's your equivalent point. And that at that point, you want to know the volume, because the volume of the sodium hydroxide times the concentration of sodium hydroxide is the moles of sodium hydroxide. Let me show you salt B. This is the titration curve for that. Let me make this bigger. Okay, so this is the titration curve for salt B. Again, there's 2 inflection points, but the first inflection point right here is what you want to read, where this inflection point, because that's the titration of hydrochloric acid. Finally, let me show you salt C. It looks like that. Okay, so again, it's going to be the first inflection point. So if you go back to the ethylene diamine analysis, what you will see is that I leave the volume at the equivalence point blank in each one of these. It's up to you to analyze that titration curve and figure out what the equivalent volume is. Once you do that, then you can do your analysis as to how many moles of hydroxide. If you know the moles of hydroxide and you know the excess hydrochloric acid you have, if you subtract these 2 numbers, you know how much hydrochloric acid did react. If you divide that by 2, then you know the ethylene diamine. So that's your ethylene diamine analysis. The last part is your nickel and sulfate analysis. Remember, I told you this was based on a calibration curve. Well, these are the values in an Excel spreadsheet. Since it's already in an Excel spreadsheet, then you guys don't need to type it in. All you've got to do is take these 2 and then generate. Here, let me show you how that goes. Just highlight it. If you have the Excel program, go to Insert. I'm going to do a scattered plot. And then this is basically it. This is the equation. All I got to do is add a trend line to this. So see, half the work is done for you because the data point's already there. I got to make sure it's a linear. I got to show the equation. I got to show the correlation factor for this. Here it is right here. Okay, so you guys are going to be doing that in the workout portion. But since the data is already there, you can see that half the battle is done for you. Once you have this, you can get the equation of the line, which should match this, by the way, should match this right here. And then you want to do a linus on this because I want to see what your true slope is, what your true intercept is, and then the errors on that. Once you have the equation of the line, this is your data for your different salt. This is the mass of the nickel for salt A. This is the mass of the nickel, the mass of the salt, rather, not the mass of the nickel. This is the nickel analysis, okay? But this is the mass of the salt for salt A. This is the mass of the salt for salt B. This is the mass of the salt for salt B. What you did was you put sulfuric acid, and then you put it in a 25 ml vol flask, and then you measure the absorbance 3 times. And these absorbance are right here. So if you know the absorbance according to Beer's law, then you can plug it back into this equation right here. You can see that the absorbance equals this value times the concentration plus the intercept. You're going to back calculate the concentration. That's the concentration of the nickel. So for each absorbance, you're going to use the equation of the line. You're going to use the intercept and the slope to calculate the concentration of the nickel. You will get an average, and then you can figure out, if I know the concentration of the nickel and I know the volume, then I can calculate the moles. If I have the moles of the nickel for each of my sample, then I can convert it to mass using the atomic weight of nickel. If I have the mass of the nickel and I know the mass of my sample, then I can calculate the percent nickel in that sample. So that's basically what this data will provide. And that's basically the data table. You want to be able to calculate these. Once you have these values, that is, you have the percent ethylene diamine, the percent of the nickel, the percent of the sulfate, and the percent of the water for each one of these salts, then you can back calculate the formula for each salt. See, for every nickel that you have, for every 1 mole of nickel, you have 1 mole sulfate. They have to exist in an equal ratio because nickel's +2, the only other chemical that's -2 to balance that out is your sulfate. So the moles of the nickel and the moles of the sulfate are the same, but the mass are not, because the atomic weight of nickel and the molar mass of sulfate are different. The moles are equal, but the mass is different. So this right here is the data for the synthesis part. The first mass there is your starting material, 1.2801. The second mass there is the product, and this is for salt A. So let me go to my iPad and let me try and explain this so that you guys can see what's going on in terms of this calculation. At this point, you should see both. You should see Canvas on the front and my iPad in the background. So what you have here is the following. You have the starting material, and then you have the mass of the product. So when you have the mass of the product, this is your synthesis. You're starting out with nickel, hexa-aquo, so there's 6 waters, and sulfate. So that right there was the amount for salt A. If you read salt A, you use 1.208. So that was 1.2801 grams. Then you reacted with ethylene diamine, and we're going to use En as a substitute for this structure right here. This is your ethylene diamine chemical. It's got a lone pair here. But you can see that it's taking me quite a number of time to draw this structure. Rather than keep drawing this, I'm going to shorthand this to be this right here, where these carbons, these two are the same right there, and then the hydrogens are not written in, okay? Just as a shorthand notation. So, this, and then I can represent this ethylene diamine. Sometimes we abbreviate it just as EN. So when we do that, we're going to get salt A. And salt A could be one of the 3 salts. I imagine you already know what salt A is, but it's one of the 3 salts. And in the analysis portion, you guys are going to determine the molar mass. Okay. And the reason why you need to know the molar mass is because if you don't know the molar mass, then you can't calculate percent. You can't calculate a theoretical yield. The reason why you need a theoretical yield is then you can calculate a percent yield. Let me remind you from Chem 200 what a percent yield is. A percent yield tells you the efficiency by which the synthesis was done. It equals the actual. And the actual in this particular case for salt A is 1.2582. That's shown right here. Shown right here in this data sheet. Okay, 1.2582. That's your actual divided by the theoretical. But the theoretical you don't know because you don't know the molar mass. Let me just remind you that the molar mass for this chemical right here is about, let me double check. The molar mass of that chemical would be about 282. Let's say it's about 282.0 grams per mole. It's somewhere around that ballpark, okay? So to calculate the theoretical yield, you know that we started out with 1.28 grams of the nickel salt NiSO4 6 waters. And the molar mass for that, we just said, was 282.0 grams per mole. Okay. So that grams that we started with is converted to moles of your starting. And in the balance equation, it's a 1-to-1 ratio because for every 1 starting material that you have, you form 1 mole of that product because the nickels are going to be the same. You're going to assume that you lose no nickel. And so the nickel, because this is in excess, is your limiting reagent. So it's a 1-to-1 ratio. It basically tells you that it's 1 mole of nickel sulfate hexahydrate to 1 mole of salt A. Okay, but in order to get mass, you need to say that 1 mole of salt A has X grams, and that's the molar mass right there, grams per mole. That's the molar mass of salt A. So until you calculate the molar mass of salt A, you can't do this calculation. You need the molar mass of salt A, and then if you have the molar mass, grams per mole, then you can calculate the theoretical yield. If all the starting material was converted to products, 100% efficiency, then this mass right here would be the mass that you would get with 100% efficiency. That's the mass, that's the theoretical yield that you would calculate in here, and then you can calculate the percent yield, which is part of the calculation. Okay, so that's what the analysis portion is. You got to figure out what the formula of the chemical you have, what is the formula of the salt, so you can calculate the molar mass. And the formula is going to be nickel, and it's going to have an ethylene diamine. And remember that I'm substituting this structure for this chemical right here. So rather than write this tedious structure, I'm just abbreviating as like that. So in one case, you're going to have two of the water being substituted for that ethylene diamine. There's going to be a counter ion, SO4. So the structure will be 4 waters, 1 ethylene diamine, and 1 sulfate. But you got to remember that this chemical might also have hydrated water. So the total water would be 4 plus Y. That'll be the total waters in your structure. And until you do the analysis, you don't know what Y is. Okay, that's why we do the analysis. The other chemical, maybe salt B or salt C, would be nickel, nitrogen, 1 ethylene diamine, 2 ethylene diamine, and then 2 waters still remaining. You're going to have a sulfate, and you're going to have water. Now, this water here and this water here may be different. One salt might have 4 waters involved. Another salt B might have only 2 waters or no waters at all. That's why you guys are going to do the calculation. And then finally, the last possible compound that you guys are going to have is the following. You have a nickel, and then all the waters are going to be replaced. And again, I remind you that when I draw these weird nitrogen with a bridge, it's because I'm trying to show you the shortcut method of drawing this structure. And then these wedges tells you it's coming out of the plane of my display, and the dash tells you it's behind. So this right here around that nitrogen, it's octahedral. Up and down, and then 4 in an axial plane. And then this also has a sulfate. The reason why all of these have sulfate is because nickel's +2 in all of these. Okay, and sulfate is -2. The only 2 chemicals that are charged in your reaction is the sulfate and the nickel. Nickel's +2, sulfate's -2. So they have to counterbalance each other if they're going to form a solid product. If you don't have that ion, you don't have anything to neutralize that ion, you're not going to get a product. It's going to be suspended in solution. And then this too also has hydrated water. And this hydrated water, Y is a number. Y is 1, 2, 3, or some whole number. Okay. That's why you do the analysis to calculate that. So what does the analysis?
Professor?
Yes.
I have a quick question. In the lab manual, it says Y is 0, 1, 2, or 3. So could it be 0?
Yes, it could be 0. Exactly. Which means that it's perfectly dry and there are no hydrates. Exactly. So Y could be 0, 1, 2, or 3, or 10. Okay. I don't think I give you that in this particular, since I'm the one that generated the data, but certainly it's going to be 0, 1, 2, 3, or some number less than 5.
All right, thank you.
Okay. So let's take a look at the data again, because I want to make sure that you understand. So that's what these values are. These are the synthesis. For salt B, in that procedure, you didn't use 1.2801, you used 1.2752. And for salt C, we use 1.0037. And this column represents the mass of the product. So hopefully you saw in the animation that I did, the amount of green crystals are these, because this chemical is green. And then the blue, The purple and the violet are these. So I tried to color code it for you so it's easy to remember. Okay. So let's move to the next data set. This is the titration of the ethylene diamine. And again, look at the salt. It's blue, purple, or violet. Let's work with salt A. In this particular case, you have to use the titration curve in order to find the equivalent volume. So there's an exercise in there where you're looking at the titration curve. The titration curve looks like this. Let me try and explain to you why that titration curve looks weird. Let me see if I can't scroll down to that titration curve. Here it is. Okay. Look at how weird that titration curve is. It's not the classic titration curve that you guys have seen, where there's one inflection point like that. Okay. What you see in this titration curve is a titration curve that looks like this. And so you might say to yourself, hey, it's got two inflection points. It's got two inflection points, and it does. But remember that, let me try and describe to you again what you did in the synthesis of ethylene diamine. Okay, let's take one of these salts. Let's take this one, for example. Okay, so let me walk you through this particular procedure. What you did was you took this salt right here, and I'm going to make it even an abbreviated portion by just showing an arc between the two nitrogen, but that arc represents that guy right there. And then you have water. Water is H2O, so I show that it's bonded to the oxygen. In this particular case, you add an excess amount of hydrochloric acid, an abundant amount of hydrochloric acid. What hydrochloric acid will do is it's a very strong acid. Let's say that you have 2 of these in your solution based on the mass that you weighed out, and then you added 10 of these, just so that you have numbers to play around. If you add 10 of these, then it takes 2 hydrochloric acid to protonate each nitrogen. What happens is that the hydrochloric acid, because the nitrogen portion on the ethylene diamine looks like an ammonia. Okay, it looks like an ammonia. Because it looks like an ammonia, that lone pair right there is going to attract the hydrogen. And when that happens, it breaks away the bonds between the nitrogen. Yeah.
I don't know if you were writing something somewhere.
I am.
Okay, cool.
Again, let me show you that down here. This is where I started. Let's say you added 10 hydrochloric acid because you're adding an excess, but you have a limited amount of nickel because you only weighed about, I think in this particular case, 0.05 grams. Okay, so the nickel is your limiting. You have an excess amount of hydrochloric acid when you add it. That's to prepare the solution. But look what happens to ethylene diamine. Ethylene diamine is like ammonia. It's got a lone pair in there. Okay, it's got a lone pair in there. And the hydrochloric acid wants to be attracted to that lone pair. When it protonates that nitrogen in ethylene diamine, it breaks the nickel nitrogen bond. And in fact, it takes 2 hydrochloric acid for the 1 ethylene diamine. It's a 2-to-1 ratio. 2 hydrochloric acid for every 1 ethylene diamine. If you have 2 ethylene diamine, like in this case, then for every 2 ethylene diamine, you need 4 hydrochloric acid. Here, for every 3 ethylene diamine, you need 6 hydrochloric acid, mole-wise. But it's basically a 1-to-2 ratio. It takes 2 hydrochloric acid for every 1 ethylene diamine. And that's important. And the reason why it's important is because the protonation causes these ethylene diamine to be protonated, and now they won't take on any more hydrogens. But you have, see how we have 10 here, and we have one ethylene diamine here. So what is unreacted would be the 8 hydrochloric acid in excess. Okay? If you read the procedure, you will see that in the ethylene diamine analysis, you take a mass of your salt, you put it in a container, and then you add an excess amount of hydrochloric acid. And that excess amount was 10 milliliters, and the concentration was 0.1944. So that was according to the direction, 10 milliliters, and the concentration was 0.1994 moles per liter. So you can calculate, based on that data, the moles of hydrochloric acid added. Okay, that's the excess amount. That's like the 10 that you added here. Some of it will react with ethylene diamine. Some of it will go unreacted. The unreacted portion is not going to be neutralized by sodium hydroxide, NaOH. Okay, so the unreacted portion, the portion that's floating around, in your beaker, you've got in your beaker the ethylene diamine that is protonated, and now you have hydrochloric acid that went unreacted. Well, when you add your sodium hydroxide to that, the sodium hydroxide is going to react with your strong acid, because that's what it wants to do. A strong base and a strong acid are going to react very complementary to each other. That's what you see in this titration curve. Let me go back to this right here, and then remind me if I don't switch back. What happens is that you're using methyl red as your indicator, okay? Methyl red changes color at about 4.22. Definitely by 5, all the hydrogen has been removed so that it would go from yellow to pink. Hopefully you saw that in the movie. At least I videotaped that. So this is the titration right here. This is the titration right here. You follow my mouse. The reason why you have this second inflection point is because now, let me go back to my iPad. All the hydrochloric acid has been neutralized. In lab, you would just stop there. You would stop where the solution turns pink and then record that volume. In this data set, I actually went past the equivalence point for that first, because I wanted to show you that when you add sodium hydroxide is a strong base. The hydroxide is going to look for any chemical in that solution that will offer it some hydrogen. Guess what? This ethylene diamine that you have, that was just protonated by hydrochloric acid. That chemical, that chemical right there can deliver hydrogen to the hydroxide. And so that's why you see the second inflection point right there, is because now it's the hydroxide is going after the ethylene diamine. But that's not what we want. We want this, because this right here is going to be the moles of the excess acid. So that's where you want the equivalent volume. Let me go back to my iPad. So let me remind you again what's going on. You have a titration curve that looks like this. So this inflection point right here is where the hydrogen is neutralized by the sodium hydroxide, the excess. This equivalent point right there is where the ethylene diamine is neutralized by the hydroxide. You don't want that. You want this first one, okay? Because once you know the moles of the base here, then you know the moles of the acid unreacted. And why do we want to know the moles unreacted? Because then we can go back here.
Professor?
Yes.
Right at the beginning, what happens with the sulfate when you titrate hydrochloric acid? Does it just pretty much dissolve and it's irrelevant?
Yes, it's a spectator. Exactly. Exactly. The sulfate doesn't do anything. So don't worry about that. Okay. All you're doing is acid-base chemistry at this point, and the only chemicals that are going to be playing a role is the ethylene diamine, the base that you're adding, and then the excess acid that you have. We want this right here, and you want to estimate the equivalent volume the best you can for your salt. Right here is the inflection point. Don't use that. So, as I said, when you have some of it reacted with ethylene diamine, some of it went unreacted. The unreacted was what you analyzed in your titration. So in the titration of sodium hydroxide, you want the volume at the equivalent point, and you want the concentration of your sodium hydroxide. And the concentration of your sodium hydroxide was like 0.0969, something like that, okay? It was supposed to be about 0.1, but we got it to about 0.0969 moles per liter. That was the concentration. So if you take the concentration of your base and you multiply by the volume at the equivalence point, okay, and that for you guys, if you take a look at for that first salt, it was around 17 something. That right there will tell you the moles of your hydroxide that reacted with the excess hydrochloric acid that didn't react with ethylene diamine. So this moles of hydroxide is equal to this moles of acid that didn't react. So why is that important? Because now you can take remember that when you added your hydrochloric acid, you used 10 mils of 0.01944 moles per liter. That's how much acid you add. Well, that's the total. If you subtract the amount that was unreacted, and that's this right here, and that's from your titration, moles of sodium hydroxide times the volume at the equivalent point, that's the amount that went unreacted. If you subtract the amount that you added from the amount that is unreacted, equals the amount that reacted with ethylene diamine. And since it takes 2 hydrochloric acid for every 1 ethylene diamine, this value right here, if you take this amount and divide it by 2, that's the amount of ethylene diamine in your compound. So these are all moles. These are all moles at this point, okay? You have the moles of excess, you've got the moles of unreacted, you have the moles that reacted with your ethylene diamine. If you take those moles and divide it by 2, that's the moles of your ethylene diamine. The next thing you need to do is you need to convert the moles of ethylene diamine to mass of ethylene diamine. Convert the moles to mass. And how do you do that? You know, if you have the moles of ethylene diamine, the molar mass of ethylene diamine, you guys already know that because I asked you to look that up in your pre-lab. That's about 60.1 grams per mole. So that's the mass of ethylene diamine in your analysis. Hopefully you guys are following me, okay? Let me go back. You put in, you weighed a certain amount of your salt, A, B, and C. These are 3 separate experiments. Then you take the mass of your salt and you weighed at about 0.05 grams. You put 10 mils of hydrochloric acid. 10 mils of hydrochloric acid at a concentration of 0.1944 tells you the moles. Part of that hydrochloric acid reacts with ethylene diamine. Part of it did not react. They were in excess, okay? What you did was you titrated that excess. That's why it's called a back titration with sodium hydroxide, and you found the equivalent point. Using the equivalent point of the sodium hydroxide and the concentration of the sodium hydroxide, you got the moles of sodium hydroxide. That moles of sodium hydroxide is equal to the moles of the hydrochloric acid that didn't react with ethylene diamine. So if you take the amount that you added and you subtract the amount that went unreacted, then you can calculate the amount that did react with ethylene diamine. That's this right here. That's the moles. These are all mole values. And if you divide that by 2, then you have the moles of ethylene diamine. You can convert that to grams of ethylene diamine using the molar mass. And then what you want to do is mass for the analysis. So let me switch view here and take you back to the data sheet. If you look at the data sheet, this is your ethylene diamine analysis. It tells you what mass for salt A you have. It's 0.0515 grams. So you now have a grams of ethylene diamine. You now have the grams of your salt. So if you take the grams of your ethylene diamine and the grams of your salt, that right there times 100 is the percent of your ethylene diamine in salt A. And why do you need percent? Because the percentage will tell you what portion of that chemical is ethylene diamine. You need to remember this value right here, okay? So that's the ethylene diamine analysis. We're not done. We still have to do the nickel analysis. Nickel analysis will be easier, okay? Hopefully you guys are following me through that. And there are 3 salts right here, 1, 2, 3. And all you need to do is come up with the average equivalent volume so that you can calculate the amount of hydrochloric acid that did not react. So let's go to the nickel analysis next. This right here is your data for your nickel analysis right here. And your lab manual originally called for just creating 3 standard solutions. What I've done was I created 5, okay? And for this particular experiment, this is what happened. You see these right here? These are the concentrations of the nickel, and then you record the absorbance. And so this was the stock solution. Solution number 5, and these were created based on this stock solution. So let me explain what's going on here. Let's go back to the iPad. So you weighed about, according to this right here, you weighed about, let me just see. Oh, you weighed about 1 gram of NiSO4 6 waters. This is your starting nickel. This is your green starting material. And the reason why we're using the starting material is because the starting material has nickel in it. So we take about the 1 gram And we prepare about a 50 milliliter solution. And in this 1 gram of sample, we add sulfuric acid, H2SO4. And then we dilute to the mark. The sulfuric acid is important because the sulfuric acid will take your nickel sulfate and make it ions. Okay, it'll make it ions. So there's just nickel sitting on here. The green color of that solution is the nickel in the solution. What you have is a certain concentration of nickel based on the mass of your starting material, the molar mass, use the molar mass, which we said was about 282 grams per mole. So if we have the mass that we weighed out, 1 gram, and we divide by the molar mass, then what we have is the moles. And then remember that we're forming 50 milliliters of that. That's 0.050 liter. So we have a concentration. That concentration is the stock solution. That stock solution, now we're going to use certain aliquots to prepare diluted samples. Okay, so now we have our stock. This is your highest concentration. And then we have diluted samples. And based on C1V1 equals C2V2, we can calculate the concentration of all of these. So in our data sheet, let's go back over here. Let me show you. These are the concentration. For the lowest concentration, the concentration of the nickel was 0.1521 moles per liter, because we can use C1V1 equals C2V2. The second is 0.03044. Third is 0.04566. Fourth is 0.06087. Anyway, these are the solutions. The next thing we did was we took these solutions, all 5 of these, we put it in a cuvette, and we measure the absorbance. We measure the absorbance. And the absorbance will look like this. And the absorbance sitting around 500 nanometers. And depending on the concentration, that absorbance will increase, because the absorbance is going to be a function of the concentration. So we're sitting at about 500 nanometers. We're reading the absorbance for all of these solutions. And now we can plot the absorbance versus concentration. And that's the data that you see right here. That's the data that you see right here. The concentration absorbance. And if you look over here, I don't give you that chart, but you guys should generate the calibration curve using the Excel data that's here. If you download this is a Excel file, so you can just basically generate the calibration curve based on the Excel file. Anyway, you're going to get a calibration curve that looks like this. And this is going to be your stock. It's going to be the highest concentration. It's going to give you the highest absorbance. Get the equation of a line. The equation of the line will be the absorbance is equal to some slope times the concentration of your nickel plus an intercept. Y equals mx plus b. And if you look at your data, I actually give you that. If you look real closely, this is the original data from this instrument. This is the concentration. These are the absorbance reading. The instrument actually takes 3 and takes an average of that, so it can give you a standard deviation. And then it does a linear regression for you. So this is the equation. When you guys take this data and you do when you plot this, it should be very close to this right here. Okay, and the reason why this is important is because now you can go back and you can record the absorbance of your salt. In salt A, I took 0.2508 grams. I put it in a volumetric flask. I think it was like a 25 ml volumetric flask. And then I took samples of that. I took 3 samples of that and I recorded the absorbance. So what can you do with that? Now that you know the absorbance, then you can back calculate from this calibration curve. Now that you know this would be your salt, it'll give you an absorbance reading. You can use the calibration curve, or you can use the equation of the line. Plug in absorbance in here and solve for the concentration of the nickel. And that'll tell you the concentration of the nickel in this sample right here. In this sample right here. Now, why is that important? Because with the concentration of the nickel, okay, the concentration of the nickel, remember that we had the absorbance spectra. You recorded the absorbance of your nickel salt. That's this right here. Using the equation of the line, you can calculate the concentration of the nickel. Remember that the concentration of the nickel is the concentration in this volumetric flask. That's that. If you take the concentration of your nickel, which is moles per liter, and that's from this right here, and you multiply by the volume of this flask, and that, let's say that that flask was about 25 milliliters, then that'll give you the moles of the nickel. So using the calibration curve data, you can calculate the concentration of the nickel in the sample that was prepared, and using the volume, you can calculate the moles of the nickel. Now, why is the mole of the nickel important? Because then you can calculate the mass of the nickel. You can calculate the mass of the nickel from the moles of the nickel. You can calculate the mass of the nickel using the atomic weight of nickel, which was about 58 grams per mole. So we have moles of nickel, and we know that the atomic weight of nickel is 58.0 something grams per mole. Then we have the grams of the nickel in the original sample, and the original sample was 0.2508 grams. So this is the grams of nickel in 0.2508 grams of sample. Now, why is that important? Because now, show you that again, I forgot. Okay, that's this right here from your calibration curve is going to be in the 0.2508 grams of sample. So if you take your grams of your nickel from your absorbance and you divide it by 0.2508 grams times 100, that'll give you your percent of your nickel in that sample. So far you have your percent of ethylene diamine and you have your percent of nickel. Okay, remember that the 4 component in this analysis is ethylene diamine, nickel, sulfate, and water. Well, how do we solve for the sulfate? Well, we know that for every 1 mole of nickel or 1 atom of nickel, we also have 1 molecule of sulfate. It's the same because nickel is +2, the sulfate is -2, so they have to exist in the same ratio. That's a given. So the moles of the nickel here is also equal to the moles of the sulfate. That's critical because if you don't recognize that, then you don't recognize the fact that you can't do the sulfate analysis. So this is key in solving the moles of the sulfate. So once you have the moles of the sulfate, let me clear this down here. Okay, clear this down here so that you guys can see that. Once you have the moles of the sulfate, which is equal to the moles of your nickel from here, then you can take the molar mass of the sulfate, which is about 96 grams per mole, and you can calculate the grams of the sulfate. Once you have the grams of the sulfate, if you divide the grams of the sulfate and you divide it by the mass of your sample, and the mass of your sample, I wrote it down over here, 0.2508, okay, 0.2508, that's this value right here. And you multiply that by 100, that right there is the percent sulfate. So the nickel analysis gives you the nickel and the sulfate. Let me clear this up one more time. So from this point on, you have percent ethylene diamine. That was from the ethylene diamine analysis. You have your percent of the nickel. This is from your nickel spectroscopy. Analysis, percent of your sulfate, which is also from your nickel analysis. And then you also have water, which you don't have, but the percent of water, oops, sorry. This whole thing should add up to 100%, okay? Because those are the only components in this particular synthesis. You know this, you know this, and you know this, and you know it has to add up to 100%. So your percent water is equal to 100 minus percent ethylene diamine minus percent nickel minus percent sulfate. That right there is your percent water. And everything should add up to 100%.
Professor Garces?
Yes.
Where did you get, so the grams of, earlier you had the grams of sulfate divided by 0.2908. Where was that one from?
Okay, let me go back to that. Okay, sorry, I can't scroll back to that because in this particular case, it's just a pad that clears things up. But make sure you let me know if you get lost in my calculation. That way I can clear things up. Remember in the absorption, that's the second part, data, we were able to get the moles of the nickel. Okay, the moles of the nickel comes from the calibration curve because we read the absorbance of the nickel of our salt, and using the equation of the calibration curve, we were able to calculate the concentration of the nickel. If we have the concentration of the nickel, we know the volume of our volumetric flask, we can get the moles of the nickel. So that's the key right there, the moles of the nickel, and that's equal to the moles of the sulfate. Why are they equal? Because if you look at the formula for all three salts, the nickel and the sulfates are the only chemicals that are charged, and they exist in all three salts in equal amounts. So the moles of the nickel and the moles of the sulfate are equal. That's the key. Once you buy into that, then you can take the moles of the sulfate, okay, which is again equal to the moles of the nickel, and you use the molar mass of SO4. SO4, the molar mass, molecular weight of SO4 is 96.0 grams per mole. So 96.0 grams per mole, that equals the grams of the sulfate. once you have the grams of the sulfate, remember the sample that we use in this analysis was 0.2508. That's the mass we use for salt A. So if you take the grams of the sulfate, which is the mass of sulfate in that sample, and divide by the mass of the sample, that's the mass in which I did my analysis, times 100, that is equal to the percent of the sulfate.
Sorry, it just looked like your 2908, it looked like a 29, and so I was confused by that number.
It's 25. I apologize. I should write on top and don't put too much pressure. But are we good in that? In terms of what I'm doing here?
Yeah. Yes.
Okay, good.
Hi, Professor.
Yes.
Would I be able to sorry, I'll put it in the group chat because it's kind of loud where I am right now.
Okay. I will have this recorded and you can follow it and rewind if you need to. Is that good? Okay.
Yes, actually, I was just going to confirm where you got the absorbance versus concentration graph. Is that just from the data you have from the
it's
the table
this
right there?
data right here. Yeah, it's this data. This is the absorbance versus concentration. And then once you establish this calibration curve, then these are the absorbance for the salts.
Okay, and the data you used to establish the concentration curve was created from just like the normal solutions, right? And it's put in that part.
Yes.
Right?
Yeah, right.
Okay, cool.
Thank you. This data right here was just from normal solutions. This was not the salt. This was your nickel starting material, because all you're doing is monitoring nickel concentration.
Okay, cool.
You're monitoring nickel concentration. Sure. Let's go back here. We're almost done, okay? We're almost done. The rest of this is chemistry 200. But let me remind you, if you forgot, if you've got the percent of the nickel, if you've got a percent of your sulfate, if you got your percent of your ethylene diamine, if you have your percent of your water, and by the way, all of that should add up to 100. When you do this in real life, if you were doing this, it would not add up to 100 because there's going to be experimental error, but I gave you data that should add up to 100, okay? Assume 100 gram sample now. Now this is independent of all this mass of compound that you just weighed. You now know the percentage of each component in your salt. That's this right here. Because remember the formula? The formula is NiEnX H2O 6 minus 2X SO4. That's the formula. So we've got an ethylene diamine right here. We've got a nickel right here. We've got a sulfate right there, and we've got water right there. So we need to know what are the ratios by which these chemicals exist. So if we assume 100 gram sample, then we can say that this percent is now this grams of nickel. This percent is now this grams of sulfate. This percent is now this grams of ethylene diamine. And this percent is now this grams of water. You just convert your percentage straight to mass. That's why we assume 100 grams. Then you use the atomic weight of nickel to convert their grams to moles. Okay, use the atomic weight or the molecular weight of sulfate to convert their grams to moles. You use the molecular weight of ethylene diamine to convert their grams to moles. And you use the molecular weight of water to convert their grams to moles. And these moles are not the same as the moles that you previously had, because the moles from what you previously had was based on a certain mass. These moles are based on a 100 gram sample. Guess what? That exactly is the mole ratio in your formula. What you want to do is now normalize this to the lowest common denominator, and that should be either be nickel or sulfate, because that's the ones that's going to be the lowest ratio. And now you would come up with the formula. You would basically take the most of the nickel, most of the sulfate, most of the ethylene diamine, most of the water, divide by the lowest, so you can get whole number integer. But that's the key to your calculation. You do all those analysis so you can figure out the percentage of each component in your sample. Each of the components should add up to 100. Assume 100-gram sample. Assume a 100-gram sample, and then figure out the mole ratio of each one of them in a common sample, 100 grams, because that mole ratio now gives you, guess what? The chemical formula. Once you know what the chemical formula is, then you can remember that the water is in excess. So if you calculate, say, ethylene diamine is 2, let's say that in this sample, you assume ethylene diamine is a 2 moles, but your water is, say, 7 water. When you make these things whole number, you've got to remember that if X equals 2, then the amount of water that you have to commit to the bond of the nickel is 2, because 6 minus 2x, 6 minus 4 is 2. That means that of this 7, 2 is going to be bonded to nickel, and then there are 5 waters that are hydrated. So if you calculate the ethylene diamine as 2, then you would have this. And then you have a sulfate in here as well. Sorry, I'm running out of space. So you have 1 nickel, 2 ethylene diamine, 2 waters, 1 sulfate, but the total water is 7. So 2 has to go to the nickel, 5 has to be hydrated. Nickel is your biggest, water is your biggest error, and that's why we put the hydrates out there. In case you have excess water, that's where it goes. That's basically the calculation for this. It's pretty involved because there are many parts, but all these is chemistry 200 stuff. It's basically just calculating moles, and it's calculating percent based on the part of each component divided by the part of the sample that you have. Okay, so sit on this a little bit, let it percolate in your mind. Maybe when you do the calculation, hopefully you were doing it while we were talking, but as you do the calculation, maybe review this Zoom video, rewind it if you have to. But that basically is it. What you want to do is get, because you guys didn't do the experiment, you should be able to calculate all 3. The calculations are exactly the same, so it's not added work. It's not like you're adding new knowledge. The calculations are exactly the same. You just have different numbers, and then that will be the resulting calculation part.
Professor?
Yes.
Quick question. The 7 is like the amount of H2O you calculated, and you have to allocate it to the Y and the H2O. That's
Exactly.
part of the complex?
That's part of the complex, right? The 7,
okay.
2 would go to the complex, and then 5 would be the hydrated. That's the part that's sticking to the salt. Okay.
Okay, thank you.
Very good point. So